Hello, you're welcome back. Let's continue from where we stopped. Now we are going to be discussing another important phenomenon on rectilinear motion. So we're going to be discussing acceleration. Okay. So acceleration, of course, by the symbol A, is giving us the change in distance with time, the rate at which velocity actually changes with time. So change in velocity, then with respect to time. All right. So let's say the initial velocity or speed of that particular object is v. The initial speed is v1 and the final speed is v2. So the change in speed is going to be v2 minus v1. All right. Then of course divided by the time to which that actually happens. It can be t2 minus t1 or simply t. So the SI unit of acceleration is meter per seconds square. All right. So I hope that is well understood. Now, okay, let's discuss uniform acceleration. So when is acceleration set to be uniform? Okay, now when an object actually speeds, okay, when the speed of an object or the velocity increases, all right, and of course the velocity increases uh, in a constant rate at all points, then such motion is said to have a uniform acceleration. Okay, so invariably, okay, so when uniform acceleration is okay is better still. Okay, let me put it this way. An object is said to have a uniform acceleration when acceleration at all the points, okay, at all points during the journey is actually constant. All right. So at uh, at any time in the journey, the acceleration is constant. When the acceleration is constant at any time in the journey, then such um, an object is said to have uniform acceleration. Okay, please take note of that. So I can actually draw a graph to illustrate that. So if this is actually going to be velocity and this is time, then drawing the graph of velocity against time, I'm going to have a straight line graph. So this straight line graph actually describes uniform acceleration because at any time, all right, in this journey, the acceleration being the slope of this particular graph, the slope which of course is a change in velocity with respect to time, is equal to the uniform acceleration. Change in velocity with respect to the change in time, and it is constant. So at this point, the value we have for acceleration at this particular point is the same as at this point. So at any point, all right, at any time during the journey, the acceleration is constant. So such an object is said to have uniform acceleration. But there's going to be a time in the journey of of that particular object where the acceleration is zero. Okay, so let me call that zero acceleration. So an object is said to have zero acceleration when at any time, right, or any interval of time when the speed or the velocity is constant. When the velocity is constant, the velocity is not changing. Remember, acceleration is as a result of a increase in velocity. So when the velocity is constant, that means the velocity is not changing, then definitely that object will have no acceleration or zero acceleration. The reason being that, okay, so the reason being that we know that acceleration is equal to uh, final velocity minus initial velocity, then of course we respect divided by time. So if final velocity is equal to the initial velocity, then the change in velocity, the change in velocity is equal to zero. And of course, 0 divided by time will be equal to 0, okay? So to represent that in a graph, how do we represent that in a velocity time graph? Velocity then versus time. So Such can be represented by a horizontal line. Okay, let's say the velocity, we have the velocity being v. So if I use a horizontal line to actually indicate that the velocity is the same. So at this point, the velocity from 0, let's say to this point, to t1, the velocity is the same. So at that, okay, during this period of time, we see that the object is having no acceleration. Okay, why? Because the velocity at this particular point, the velocity is constant. So because the velocity is constant, then the change in velocity is equal to 0. Okay, all right, then we now look at uniform deceleration. Okay, so the word deceleration actually means uh, uh, a decrease in speed. When the speed of an object is decreasing, it's decelerating. All right, so which simply means that in such a case, we discover that um, the final speed is actually final speed is less than the initial speed. That means the speed is decreasing. All right. So that actually happens during the slowing down process. Let's say you have a car. All right. So this car needs to stop at this point. So for the car to stop, all right, what happens? The driver will apply brake. Okay, so the car was actually moving at a very high speed. So at this point, it's moving at a very high speed or high velocity. So now, for the car to stop at this point, then this speed will start reducing. So that reduction in speed, all right, is what is known as deceleration. It will decelerate until the speed reduces to the point where the speed now, the final speed of velocity is equal to 0. Then we say that the car have actually come to rest. So the slowing down process, all right, is what is known as deceleration. And of course, it is having the same formula as acceleration. They are the same. That is that one is opposite the other. One is speeding up while the other is actually slowing down. I hope that is well understood. So we can actually put everything together. So we can put everything together in a velocity time graph. First, we started with uniform acceleration. Then we now have zero acceleration, which of course is at constant velocity. Then finally, the object actually returns, okay, slows down to rest uniformly. So this is uniform acceleration. So at this point, the object is having constant velocity or zero acceleration. Then this is, of course, uniform deceleration. Uniform deceleration. All right, so let's of course this object actually starts from 0. Let's look at the final velocity from 0 to v. Okay, so from 0 to the point, the object actually accelerates uniformly from 0. The velocity increases to v. Let the time for that acceleration actually be t1. All right, so at that that very time where the velocity is v, the final velocity is v, the velocity is no longer increasing. The velocity remains the same. All right, so from t1 to this point, let me call it t2, that object is still remaining, is still having the same velocity, constant velocity. So that means the object from t1 to t2 does not have any acceleration at all. All right, because the velocity is constant. Then from t2 to t3, the object actually, the speed of the object reduces, so the object decelerates to rest. So this is actually going to be this graph shows the complete motion of this object. So from here now we can calculate the acceleration. Acceleration, of course, is going to be equal to the slope of the graph. The uniform acceleration, of course, is going to be the slope of the graph. That is the line that the yellow line, of course. How do we do that? The slope of the yellow line is going to be final velocity minus initial velocity. Final velocity is v minus initial velocity, which of course is 0 from rest. Then the time is t1 minus of course initial time, which is 0. So that is v all over t1. That is the uniform acceleration. So just in case you are being you see this kind of graph and you're being asked to calculate the uniform acceleration, that's exactly how you calculate it. All right. Then of course the uniform deceleration can also be calculated in the same manner. Okay, let me bring this okay. All right, so okay, here we go. So now, so at the end of this journey, after the acceleration, the constant velocity, and of course the uniform deceleration, how can we now calculate the total distance? Total distance covered by the object. Remember from the formula, okay, we know that velocity is equal to, all right, displacement all over time, all right, which we know that displacement and distance, in as much as rectilinear motion is concerned, is the same. Okay, so we have that delta x then divided by t. So invariably, total distance, anytime you're being asked to calculate total distance, all we just need to do is to cross multiply. All right, that's going to be velocity. This velocity, remember, okay, for a uniform acceleration, the velocity, all right, is known as the average velocity. V, of course, multiplied by t. This is the average velocity. Average velocity. All right. So, but that is not exactly what we are looking at here. So invariably, for the total distance is actually is divided into into 3 different segments of this journey. First is the uniform acceleration. So this object covers a distance of course, v multiplied by t1. Second is the constant velocity. There's a distance covered here. All right. Then third is the uniform deceleration. There's also a distance covered. So there are 3 segments: segment 1, segment 2, and segment 3. So invariably, okay, the distance covered, all right, by the object will definitely becomes the area of the graph, the area of the graph, the area under the graph. And as you can see, the shape of this particular graph is a trapezium. So total distance, okay, of course, let me use x. I can use x. Okay, let me use of course, let's use this symbol. Okay, or delta x. So the total distance covered is going to be equal to the area of the trapezium. What is the area of the trapezium? Area of a trapezium is always half sum of the parallel side. Half sum of the parallel side. What are the parallel side? The parallel side is between t1 and t2. All right, and of course that is between this between the start of the, of course, constant velocity, right? That is from t1 to t2. From this point, let me change the color. From this point to this point, this is okay, this is parallel to, and from this point to this point, horizontally, okay, and we're measuring it horizontally via the the t axis, the time axis. Then you multiply by height. So the area of a trapezium is always half sum of the parallel side times height. Half sum of the parallel side times height. Okay, let's do that. Half sum of the parallel side. Half sum of the parallel side, that is half t. The first parallel side, it's a distance, right? The first parallel side is a distance from, please pardon me. The first parallel side is a distance okay, distance from t1 to t2. Okay, so let me put that in this in the formula. That is t2 minus t1. That is the first. Then plus the distance all the way from 0 to t3 plus t3. Then okay, then multiply by the height. The height, of course, is the final velocity from 0 to v, which of course is v. Okay, so multiply by v. So the usage of this formula, all this formula, is what I'm going to be showing you in the next video. Okay, so how to use it, and of course the application of this formula, right? So please take note of this, write them down, and we are going to look at some questions in the next video. So see you in the next video. Thank you very much.